Okay, Assalamualaikum and good morning, everyone. So for today, we are going to new chapter. So chapter 4 will be about root locus. Okay, so in previous chapter, we have learned about using Route-Hurwitz table or Route-Hurwitz criteria to determine the system stability without having to factorize or without having to find the poles of a transfer function. So sometimes the poles the denominator is very hard to factorize, or you require maybe a calculator to factorize the denominator. So it's hard to find the denominator and find the poles and then determine the system stability. So you can use Route-Hurwitz criterion to determine the stability of a system. But in today's lecture, we will go into learning root locus, which is another mathematical method on determining the poles. But this time, the transfer function will depend on a gain k. So in previous lecture, you have seen how to determine the range of k for a system to be stable. So in this topic, we will go into finding the poles or finding the characteristic of the transfer function or the poles when we vary the gain. Okay. So for today's lecture, we are going to look at the properties of root locus. So students will be able to aware of the control system problem, of the problem that requires root locus. And then secondly, aware about vector representation of complex number. So you have complex number so far. We have learned about poles and zeros, and these poles and zeros are in the form of complex number, meaning that it can be in terms of j, okay? Or j means square root of -1. So it's actually a form of complex number. So we can represent the complex number using vector. And then lastly, we define the root locus, and then we determine the properties of root locus. Okay, so root locus is a graphical presentation of the closed loop poles as a system parameters k varied. So it's a powerful method of analysis and design stability and transient response. So basically, you have k here. So in Route-Hurwitz criteria, you simplify the block diagram, and then you determine the denominator, and then after that you uh, use Route-Hurwitz table to determine system stability. So you only know the system stability without knowing the poles, or without knowing what is the poles, what are the poles when you have a certain value of k. So for example, k equals 5, for example. So what are the poles for the closed loop system? So with root locus, you actually use graphical representation or graph to plot the poles when we vary the k. Okay, we will see later an example. Okay, so uh, before we go into detail about root locus technique, we need to understand what are the problems that requires root locus and how to present a complex number in vector form. Okay, so firstly, let's say you are given a feedback control system as shown here. So you have forward transfer function kg and then a feedback transfer function h. So first you need to simplify this. So okay, so here when we simplify this transfer function, we have two types of gain. So the first one is open loop transfer function. So we call it loop gain. And loop gain equals kg times h. And then when we simplify the block diagram by considering the feedback, then we call this closed loop transfer function. So you use a feedback formula, kg divided by 1 plus k times g times h. Okay, so this is the formula for feedback. And this is what we call the term kg here is the forward or open loop transfer function. So when you have this transfer function, so let's say you are given a system as shown here. So when you simplify the system, the block diagram, and then you determine the time response, and then let's say you substitute different values for k. For example, you use k equals 0.5. So when you plot the time response, you will see that the graph is something like under dam. Okay, and then when you use different k value, for example, k equals 2.0, so the graph is the time response will be slightly different. So it has overshoot here. And then when you increase k, let's say you use k equals 15, then the system will be overdamp and has some damping or ripple before reaching the steady state value. So the objective here is that you want to find a suitable value of k so that your system is not too slow, like k equals 0.5 here. It reaches steady state, but it will take very long time before reaching steady state. And you also don't want to have k equals 15, because when you have k equals 15, then the system will be tak. Sorry. Okay, so sorry about that. Biasalah terkeluar. Okay, so when you have a transfer function, let's say a closed loop transfer function, so each of the G
Sir,
and
sir.
yep. Sorry. Okay.
Undur balik boleh tak? Saya explain daripada
Okay, ni.
daripada sini.
Ni. Okay, so from here, sorry about that, guys.
Sorry, sir.
Okay, so from here, your time response actually depends on the poles. So we know that it depends on poles from second order system lecture, okay, second order system lecture. And now we know that it also depends on the gain K. So when you vary the gain K, then the system stability will change as well. So there are two things that determines the system stability. First, first is the poles, and secondly is the gain K. So how we can use new method to determine what are the suitable value of K and poles. Okay. Okay, so let's say you are given a closed loop transfer function Ts here. So each of the G and H probably has its own numerator and denominator. Okay, so when you expand each G and H in terms of its numerator and denominator, okay, this is just example, okay? So you don't need to memorize, or this is not formula. So when you expand and you simplify, you will see that the denominator here is depends on K here, the gain K. So you want to determine the system stability by finding the poles. And poles can be determined by finding the roots of the denominator. So when you look at this denominator here, now the denominator depends on K here. And then let's say if you use open loop transfer function, then the denominator will depends only on the poles will depends only on the denominator, so not depends on K. So for closed loop system, it will depends on K as well instead of only only on the poles. So let's say so here uh, what I just told you just now. So for closed loop, it is a combination of the numerator and denominator of forward and feedback transfer function. And the poles also depends on the gain K. While for open loop transfer function, it depends only on the denominator only. So for closed loop system, you need to know that it depends on K. So now we need to look at new methods for finding suitable value of poles for stability. So therefore, with closed loop system, the poles are not easily obtained, and it will change with the value of K. Okay, so for example, you are given G and H, transfer function G and H. So for open loop system, you can easily determine the poles, okay, by finding the value of S when the denominator equals 0. But for closed loop system, now the denominator is depending on K. So to determine the poles, then you need to expand the denominator, and it will depends on the value of K you give, okay, to the system. So that's why we use root locus technique to help us find the poles. Okay, so before we go into understanding about root locus, we need to know about how to represent complex number using vector. So I think you have learned this back in calculus, okay, or back in diploma matriculation, okay. So complex number, let's say S equals sigma plus j omega. So sigma here is the real part, and omega here is the imaginary part. and j is square root minus 1. So we can represent complex number in terms of vector by plotting the complex number in S-plane. So the y-axis is the imaginary axis, and then the x-axis is the real axis. So we have, let's say, a vector here that represent the complex number S here. S equals sigma plus j omega. So sigma j omega here. So your complex number is at this intersection. And we can draw a vector line from the origin to the complex number. And the complex number can be represented by the magnitude of the vector and also the angle of the vector from the real axis. So it has magnitude and direction. So magnitude is equals the square root of sigma square plus omega square. And the theta, actually the angle from this positive axis to the vector. So let's say if your vector is at this section of the S-plane, then the angle will be measured from here to here. Okay. Let's say, boleh draw tak? Okay, so let's say if your vector is here, then your angle measures from x-axis to the vector. So this formula only applies for any complex number that lies only on this section of S-plane. But for other section, then you need to modify the formula. Okay, maybe you have to add 180 minus theta. Okay, so benda ni kena measure sendirilah. Okay, mungkin korang tak ingat tapi nanti kita tengok example. Okay, and then therefore when we have the magnitude and the angle, then we can represent the complex number S as follows. Okay, so we have m, the magnitude, and the angle theta. So this triangle here means angle. Okay, so m angle theta. So we can represent S from sigma plus j omega into m angle theta. All right, so let's say if you have a function that depends on a complex number S. Okay, let's say f is a function that depends on S, and you can replace the S by sigma plus j omega. So we get a new values here. So here the function f becomes a new complex number. Okay, so tak penting. Okay, so let's say you are given S equals 5 plus J times 2, and then you have Fs equals S plus 3. So what you do is you replace S with this value here. So your F will become 8 plus J2. Then when you plot, then here what this example wants to show is that when you have a complex number, a complex function F, and then you substitute the value of S with another complex number, then a different or a new complex number will form. Okay, but the complex number will be parallel, but it will start at a different origin. So here, the original complex number starts at origin 0. But when you substitute with different complex number s, then it will start at a new origin. Okay. And then you can determine the magnitude and angle of the new complex number. Okay, so to determine the magnitude, basically you determine the length of the zeros. So first you need to find the zeros and poles for the complex number f. After you find the poles and zeros of the complex number f, then to determine the magnitude is simply by finding the length or the m of each of the zeros and poles. And then you find the product. So this symbol is product. So the product of the length of 0 divided by the product of the length of the poles will equal to the magnitude of the new complex number f. So this symbol big pi here is product, okay? Product of the length of 0 divided by product of the length of poles will be equals to the magnitude of your transfer function f. And then to find the angle is simply by finding the angle of each of the zeros and also find the angle of each of the pole. And then you sum the angle of 0 minus the sum of the angle of the poles. Okay, so to determine the magnitude is simply finding the product of the length of 0 divided by the product of the length of poles. And then to find the angle of the transfer function f is simply by finding the sum of the 0 angle minus the sum of the pole angles. Okay, so let's look at the example of how we can use this formula. Okay, let's say you are given a transfer function f equals s plus 1 divided by s times s plus 2. And then you are given s equals minus 3 plus j4. So first what you need to do is you substitute s into the transfer function. So here I already substitute. So first you put s on the poles on top, and then substitute on the denominator, and then you separate them. Okay. So first you simplify the numerator, so you will get minus 2 plus j4, and then divided by minus 3 plus j4, and then in this bracket you simplify minus 3 plus 2, you get minus 1 plus j4. So from here, you determine the magnitude of each of the poles and zeros. So first we look at the 0 here. So the 0 is equals minus 2 plus j4. So to find the magnitude, basically you square root the sigma square and omega square. So sigma square you get 4. So sigma square you get 4 plus 16 and then square root. So you get square root of 20. And then the same thing for here. This will become 9 plus 16 square root. So you get 5. And this is here. And then for this one is square root of 1 plus 16. So it's here. Okay, so then you determine the product of the zeros divided by the product of the poles. So square root 20 divided by 5 times square root 17. Here ada soalan?
Macam mana kita tahu value J tu sama dengan 4?
J sama dengan 4. Ni 4. Soalan bagi kat sini. Jatuh ke soalan saya, soalan awak?
Macam mana kita tahu dia punya value of value J?
Oh, J tak ada value. J tu square root minus 1 equals J. So kita ambil sigma and omega. Ni omega and this is sigma.
Oh, okay. Tengok saya dah faham.
Okay. And then you find the product of zeros divided by the product of poles. Okay. And for the angle, you need to determine using the tangent formula, or it's easier if you can plot the complex number on S-plane first. After you plot, then you can find the angle of each of the complex number. So first complex number is -2 plus 4j. So it's -2 plus 4j. It's somewhere sepatutnya sini. Okay. So when you plot the complex number, then you can determine the angle. Okay. So to find the angle, it's better to plot the vector in S-plane first, and then determine the angle. Okay, so for example, to determine the angle theta here, macam mana buat lah, lupa dah. It's equals 90. So theta equals 90 plus tangent minus 1. 4/2. Okay. So you get this 116.6. Okay, so I think you have learned this back in first year, okay? Revise balik, okay? So you determine the angle for each of the complex number, and then you sum the angle for the zeros minus the sum of the angle of the poles, okay? So to determine the angle, it's better to plot them in S-plane, sketch in S-plane, and then determine the angle. Because sometimes you use the formula tangent, it's only suitable for the vector lies on this section, okay? On the section of the S-plane. But when the complex number lies on different section, then you need to determine either plus 90 degree or plus 180 degree and so on. Okay, so when you find the each of the m or length and angle for the zero and poles, then you can find the product of angle of the length and the sum of the angles. Yeah, sorry. Soalan apa?
Tak dapat 116.
Alamak. Saya tak ada calculator. Ada. So 90 degree plus tangent. Oh, 2/4 kot. 2/4. Oh, it's 2/4, sorry. 2/4.
2/4 dapat.
Kat sini. So this is 4. This is 2. So tangent is opposite macam ni. Pandai-pandai lah kira. Tak apa, nanti korang try lagi lah. Okay, ada exercise yang dalam quiz tu. Okay, so and then you will get the angle and magnitude for the complex number f. Okay. Okay, so so you can try quiz 11 question 1 and see whether you can understand how to find the magnitude and also the angle. Okay. I give you about 10 minutes of somewhere about that. Okay, so question 1, quiz 11, question 1. So the clue is already given. So first you substitute this S into the transfer function, and then find the magnitude and angle for each of the poles and zero, and then find the total magnitude and find the total angle. Okay, can you try first? Dapat square root 20. Maaf, slow sikit. So 2 tu Hakim dah jawab.
Mantap Kimi.
Mantap. Ouch. Sengit.
Doktor,
Hmm.
yang doktor post kat dalam group tu,
Hmm. Ya.
kalau untuk ADP macam mana doktor?
IDP korang still jalan kan? Rasanya IDP tak ada exam, so tak ada masalah. Tapi korang buat simulation kan IDP?
Dia depend pada, tak tahu lah. Ada yang kata
Pada
sama apa.
SB kan?
Kena
Kau kena
fabricate.
fabricate juga.
Yo.
Apa lagi? Sem depan lah. Sekejap, apa dia cakap sebenarnya? Bagi pelajar sem akhir saja. IDP saya tak tahu. Kalau lab saya tahulah lab tu memang TS. IDP tak tahu.
So,
Hmm?
untuk magnitude, jawapan dia berapa?
Tak kira pun. Alah, sekejap. Square root 1, alamak. 25. 0.09 tah? 0.0961.
Lain ni.
Salah ni. Sekejap.
0.01
Lain 0.1.
0.01.
0.1. 0.09. 96. So just substitute S, simplify kan, and then find the magnitude for each bracket, okay?
Di antara satu-satu tu dia kena tambah ke darab?
Kalau magnitude untuk yang ni darab dengan yang ni, and then divided by magnitude ni, darab magnitude yang ni, darab magnitude yang ni.
So, sekarang negatif 5, negatif 3, negatif 7, negatif 4, negatif 1 kan?
Nah, negatif 5, negatif 3, negatif 7, negatif 4, negatif 1. 0.09. Lepas tu ada 9 kat sini.
Tahu.
So square root 25 plus 81 times square root 9 plus 81 divided by square root 49 plus 81 times square root 16 plus 81 times square root 1 plus 81.
Pening rasa.
So kalau pening buat satu-satu. Maksudnya boleh asingkan cari magnitude ni dulu.
So saya buat negatif 5 dengan 9 dulu kan. So dapat square root 106 betul tak?
Tak tahu sebab saya sekali kan. Square root 106. So dapat dalam 10. Okay. Any question for this Any question for this question? If no, we can proceed. But you can try first, okay? Find the magnitude for each of the brackets and also
0.09
find the
tu
angle.
siap.
0.096.
Okay.
Okay, so to find the angle, first you need to, the easiest way is to plot them in S-plane first. And then after that, you only determine the angle, okay? If you want to use the tangent formula, you need to be careful because the sigma here is negative. So it lies on the left-hand side of the S-plane. So you need to add 90 degree, okay? Okay, so we move on to the next subtopic.
So untuk degree tu kita ambil yang atas je ke?
Kita ambil semua untuk degree. Untuk yang atas ni, cari degree ni, and then cari degree yang ni, and then totalkan, tambahkan, minus yang ni, tambah ni, tambah ni.
Oh, atas tambah bawah, so kita dapat dapat satu angle.
Atas ni tambah, yang bawah ni tambah,
So,
and then
tolak
atas minus bawah.
So
atas
kita akan
tolak
dapat
bawah.
Kita akan dapat satu line lah.
Satu nilai untuk F punya angle.
Right.
Okay. So root locus. So root locus ni invented by W.R. Evans 1948. Okay. Terima kasih pada dia kerana menyebabkan automatic control susah. Okay, so root locus is a graphical presentation of the closed loop poles as a system parameter is varied. Okay, so basically it's a graph of closed loop poles when you vary the value of k, okay? And then it's a method to analyze and design control system for stability. Okay, so let's say you are given an example of a camera. So this camera, you can rotate the position here. So the position is controlled by a motor, okay? So this is the transfer function of the camera. So you have amplifier gain K1, and you also have the transfer function for the motor and camera. So let's say you are given the transfer function equals a gain K2 divided by S times S plus 10. So the first step is you simplify the block diagram. So you will get something about something like this. And then you simplify K1 and times K2 equals K. So this is just example, okay? So the gain K here depends on K1 and K2. Okay? And then after that, you can find the poles for each value of K. So let's say your K equals 0. So you substitute K equals 0 and then find the value of poles. So when K equals 0, then the poles will be minus 10 and 0. And then you can repeat the process. Maybe you use K equals 5 and then poles, you find the poles and you repeat the process, okay? So here you will see that the poles is changing, okay, are changing depending on the gain K. But you will see here that as you increase the value of K, then the poles will somehow reach a value, a single value. So here it will reach -5 plus J times 5. And another pole is -5 minus J5. So you will see that it will reduce, okay? It will reduce until reaching a certain value, okay? A constant value. And then you can plot the poles on S-plane. So here is the pole when k equals 0. So there are two poles here. One here, -10, and another one here is 0. And then you repeat the plot, okay? You plot the value of poles when k equals 5. So it's here and here, and then repeat for k equals 10 and so on until k equals 50. So you will see a trend here, like a cross, okay? And then from the cross, you can connect all the poles, okay? So you connect all the poles. So it will start from here, and then it can either go down or go up. And then same thing for here. It will start from -10 and it goes to -5, and it can either go up or go down. So this plot here is the root locus, okay? So root locus, basically you find the value of poles for different value of k, sketch the poles on the S-plane, and then you connect all the poles using a line, okay? So here, the cross line here is the root locus, okay? Meaning that the root locus represent the value of poles or the poles when you change the value of k. Okay, this is the root locus. Okay, so root locus basically represent the path of closed loop poles as the gain is varied. Okay, so when you vary the gain k, then the poles will follow this path. Okay, it will start from this and then go up, and then it will start from here and then maybe go down. Okay, so it's like something similar to a graph but has direction. Okay, so it will start from 0 and then go up and then start from -10 and then go down. So what can we learn from this root locus? So when you have k in between 0 and 25, meaning that k from here to this point, and from 0 to this point, then the system is overdamped. So to prove this, you can plot the time response for each of the trans function when you have poles or gain at this line, okay? And then when k equals 25, so at this intersection here, then the system will be critically damped. And then for k bigger than 25, which is in this line, then the system is underdamped. So here, because all the poles are on the left-hand side of S-plane, then the system is stable for the value of k from 0 for value of k bigger than 0, okay? So if you have k negative value, then the system will be unstable. So all of the poles here are for stable system. So from the root locus, you can determine the stability of a system. So you can first look at where the poles are located. Okay, so here from the root locus, the poles are located on the left-hand side of the S-plane. So there are no poles on the right-hand side, meaning that the system is stable. Okay, and then you will also can see that for the poles lies on the real axis, the system is overdamped. And for the poles on the intersection here, the system is critically damped. And when the poles are on the left-hand side but has imaginary part, so here meaning that your poles has imaginary part. So when your poles has imaginary part and also on the left hand side of S plane, then the system is under them. Okay, so this is the meaning of root locus. Okay, so in tomorrow's lecture, we will go into sketching root locus in more detail. Okay, so this is just example of how to explain to you about root locus. Okay, so there are certain properties of root locus that you need to know. Okay, so let's say you are given a closed loop transfer function here. So how to get the poles? So to get the poles is basically you need to look at the denominator and then find the value of S when denominator equals 0. So to get the poles, the denominator equals 0. And then you rearrange, you'll get K times G times H equals -1. Okay, so the value -1 is a complex number, even though it doesn't have the imaginary part. So for kgh, then it equals -1. So if you plot -1 in S plane, so it has magnitude of 1. The magnitude is 1. And the angle from real axis is 180 degree. Okay, so the angle measured from x axis, positive x axis. So from here to the vector is 180 degree. So you can represent it in this form. So 1 is the magnitude, angle is 180 degree. So the magnitude is 1, the angle is 180 degree. And this is a multiplier, okay? So usually K we assume 0. But we will go into this more tomorrow, okay? So for the magnitude of the transfer function just now must equals 1, okay? And then to find the value of K, so you simply rearrange this. So K equals 1 divided by the magnitude of transfer function G times transfer function H. Okay, so this is how you want to find the value of K. And then the angle condition. So the angle is always 180 degree. So you can find the angle of, you can find the K by using angle as well. So here you can substitute K equals 0, 1, 2, and so on. But for now, we assume it's equals 0 only. So the important things here is K equals 1 over the magnitude of G times H. Okay, we look at example, okay? So let's say you are given a unity feedback system. Okay, so unity feedback system meaning that it has feedback, but the feedback transfer function equals 1. So when you are given a question saying unity feedback meaning that the feedback transfer function equals 1 or H equals 1, okay? So sometimes in your exam or in your final, you are given only the word unity feedback. So you need to remember that unity feedback meaning that H equals 1. Okay, so the question here is this point -3 plus 0j is on the root locus of the transfer function. And then if the point is on the root locus, find the value of gain k. Okay, so how to do this? Okay, so the first step is we need to determine the zero and poles of the forward transfer function. Okay, so since this is unity feedback, so for unity feedback, you can find the closed loop transfer function and then determine the poles and 0. But because there is a term k here, so your denominator will be depending on k. So for unity feedback, to find the 0 and poles is simply by looking at the forward transfer function only or transfer function G. So if I represent this into a system, then let's say this is the summing junction and this is G and output. And then unity feedback has a feedback, but the h equals 1. So when h equals 1, you just draw a feedback line only without drawing the box. So here g here is the forward transfer function. Okay. So another name for g is forward transfer function. So only for unity feedback. Okay. So unity feedback is when h equals 1, and forward transfer function for unity feedback is g here. Okay, so for unity feedback, to determine the zeros and poles, you only need to determine the zero and poles for the forward transfer function. Okay, so you need to find the zero and poles of this only. And then after that, you determine the angle from zero and poles to this point. Okay, so determine the angle from the poles and zero to this point. And then next, determine the length of vector from zero and poles to this point. And then lastly, you add all the angles. If the angles equals multiple of 180 degree, then the point here is on the root locus. And then lastly, to determine k, simply using the length of 0 divided by the length of poles. Okay, so let's look at example. This example, how we can determine this point is on root locus and the value of k. So the first step is to determine the zeros and poles of the forward transfer function and then plot on S-plane. And then also plot the point of interest. Okay, the point of interest just now is -3 plus 0j. Okay, so the first step is so you determine the poles and 0. So here the 0 is -2. And then the poles is, you can use quadratic formula, okay? Or use calculator. So you get 3 and -3. So you get S equals -2 plus -3j. So it's -2 plus 3j. So it's here and it's here. So usually you represent poles using cross X, and you represent zeros using circle. Okay, so the circle here is the 0. So 0 is -2, and the poles are -2 plus -3j. So it's the X. And then you also plot the point of interest. So the point of interest is here, -3 plus 0j. Okay, that's the first step. And then the next step is to find the angle from 0 and poles to the point of interest. So first you draw lines that connects the poles to the point of interest. So there are 3 lines. This is the first, second, and third. And then you find the angle from 0 and poles. So first you find the angle θ1. So θ1 measures from positive real axis. So start from here to this line is angle θ1, okay? Angle of this pole to the point of interest. And then the second angle is from -2. So θ2 measure from here to here. So this is equals 180. And then another angle is measured from here to this line. Okay, so then you can find the angle. So θ1 equals 270 minus tangent 1/3. Okay, so there are a lot of ways to calculate this. Okay, one of the way is 270 minus. So you can also calculate by finding 180 degrees plus this angle. Okay, practice lah macam nak kira. Okay, ada banyak cara. And then the second angle is 180 degree. And then the third angle is 90 degree plus this angle. So you get 108.43. And then after that, you sum all the angles and determine whether it is multiple of 180 degree or not. So you have three angles just now. So this is angle poles, and then this is 0, and then this is pole. So you need to sum the angle of 0 minus the sum of angle of poles. So theta 2 minus theta 1 plus theta 3. Okay, sum of zeros minus sum of poles. So 180 degree minus 251.57 minus 108.43
Sir,
equals minus 180
saya
degree je.
nak,
Soalan?
sorry sir.
Ah,
Dia memang untuk angle pulse tu, kalau kita total akan dapat 360 ke?
tak semestinya.
Kalau untuk
Tapi
untuk bentuk
untuk
ni kan,
soalan ni, yang mana
untuk bentuk
bentuknya?
ni dia akan dapat 360 lah kan?
Kalau ini dia dapat 360 secara kebetulan lah. Tapi mungkin untuk point lain, untuk point yang diberi lain, let's say -4 ke, maybe angle dia lain. So yang penting ialah bila you sum the angles, you mesti dapat multiple of 180 degree. So if multiple of 180 degree, then this point is on the root locus. Kalau dapat lain, maksudnya point ni bukan dekat root locus tu. Maksudnya point ni di luar root locus lah. So kalau kita kira dah dapat point ni dapat 180 degree, maksudnya point ni berada dalam root locus kita. Okay. So this is how you determine whether this point is on root locus or not. Okay, then we need to determine the value of k at this point. So to determine the gain k, so firstly, you need to determine the length of the vector that connects all the poles and zeros to the point of interest. Okay. So L1 is panjang garisan ni. So panjang garisan ni equals 3 squared plus 1 squared. Okay. 3 squared plus 1 squared, you get square root of 10. So for L2, it's equals 1. So the length is 1. And for L3, the same length, okay, square root of 10 as well. And then after that, you find the gain k. So you have three lengths just now, L1, L2, L3. So to find gain k, you simply equals 1 over m. So m is the sum, the product of length of poles, length of zeros divided by the product of length of zero. Okay, product of length of poles, length of zero divided by product of length of poles. So you get 1 divided by square root 10 times square root 10. So you get 1 over 10. So you substitute. So you get k equals 10. Okay. Panjang lebar. Okay, so you can try do quiz 11 question number 2 to see whether you understand, and if you have problems, just ask me, okay? So question 2, quiz 11. So you have this forward transfer function for unity feedback, okay? Determine if the point -3 plus 0j on the root locus. Macam sama je soalan tadi.
Sama je sir.
Bonus.
Tak apalah, korang buatlah sebagai latihan tanpa tengok slide. Gitu.
Alright sir.
Soalan lain dah, soalan dia ni je. Okay, so try buat ni tanpa tengok slide. Boleh faham tak? Boleh dapat tak? Ya, ketuk lah. Unity feedback tadi. Masya Allah. Ya, Unity feedback. Ni mesti baru masuk kan. Pergi makan kan. Ni Unity feedback. Unity. Pakai mouse lah. Buruk tulisan. Okay, Unity feedback meaning that the feedback here, dia punya age equals 1. Okay. Orang boleh tengok jawapan. Okay, any question? Okay, so if you have no question, then that's it for today's lecture. Okay, so we will continue more tomorrow about sketching the root locus. So in the example that I give you, example this one. So this is an example of uh, drawing the root locus by varying the value of k. But tomorrow we will learn about how we can sketch the root locus without without doing this table. Okay. So basically here you repeat the process. Do this, find the value of k, substitute value of k, and then find poles. So tomorrow we will learn about how to sketch the root locus without using this table. There are certain characteristic or properties of root locus that you need to know, and most of the time, not most of the time, I think so far all semester there will be one question about root locus. Okay, and most of the time students couldn't answer question related to root locus. Okay, so root locus is difficult and easy to lose mark. Okay, in final exam. Okay, so that's it for today's class. We continue tomorrow. Okay, so assalamualaikum and bye bye. Thank you.
Waalaikumsalam. Thank you,
Thank you,
sir.
sir.
Bye.